In this video, I'm going to go over the second learning objective of Math 245, Statistics Section 5.4. Let me go up there and read the objective with you. I already have posted the lesson video on the first 13 slides where we went over how to find sampling distribution and verifying their properties like mean and the standard deviation. Okay, the big idea from that first piece of the lesson was this. Some of you will see homework problems where you have to use this formula to find the probability, your normal calculator. And I think I went over one question that Jenny forwarded me. So I can also share that with you. So just email me about these homework questions if you are not sure how to do them. But let's do the second one. It's called How to Interpret the Central Limit Theorem. What we want is we want that sample size to be bigger than or equal to 30. We want it to be bigger than or equal to 30. If it is, then we get to use this central limit theorem. Okay? Alrighty. So let me go to slide number 14 and talk about what this central limit theorem is saying. Okay? I'm going to go ahead and present this Google slide. Alright, central limit theorem. If samples of size n greater than or equal to 30 are drawn from any population with mean of mu and standard deviation of sigma, then sampling distribution of the sample means approximates a normal distribution. The greater the sample size, the better the approximation. So what are they saying here? Do you know that not every distribution out there are normal distribution, right? Sometimes we have skewed distribution, like skewed to the left or skewed to the right, or uniform distribution that looks like a box, or it could be bimodal. Not every distribution out there is normally distributed or are normal. You agree with that, right? But what they are saying is this. If you take a sample of size n greater than or equal to 30, the sampling distribution will be approximately normal. Okay? So whenever you get these problems, I want you to check the sample size. If sample size is greater than or equal to 30, like they collected data from 100 people or 40 people, if the number is bigger than 30, then it will be safe for us to use the normal distribution to calculate some probabilities because their sampling distribution will be approximately normal. So look at the picture for me. Any population distribution. This is an ugly looking population distribution. This looks like it has a peak over here on the left, and it doesn't look normal at all. But even something as ugly as this, if we take a sample of size greater than 30, the sampling distribution from this population distribution will be normally distributed. It's a powerful theorem. So I'll show you. Hold on a second. Let me go to the next slide and see what the next one is about. Number 2. If the population itself is normally distributed, oh, this makes me so happy. Look at this beautiful population distribution. So it's like this. The parent is already normally distributed. The child or the distribution of the sample means we're going to expect that to be normally distributed regardless of the sample size. So this one, we don't really need the sample size to be greater than or equal to 30. If the population is already normal. But in the previous slide, you see how population distribution was not normal? This is the case where we need that sample size to be greater than or equal to 30. But if population distribution is normal, we don't care about the sample size. It doesn't have to be greater than or equal to 30. If population is normal, sampling distribution will be normal. So let me read number 2 here. If the population itself is normally distributed, the sampling distribution of the sample means is normally distributed for any sample size n, right? So that's good. N can be 2 for, if you want it to be. N can be 5. and it will still be normal. The sampling distribution will still be normally distributed if the population is normally distributed. So you notice there are two cases, right? From an ugly population, then you need to have a big sample size of at least 30. For a beautiful normal population, we don't care about sample size. It's going to be automatically normally distributed for its sampling distribution. So what is this then? In either case, ugly population or beautiful normal population, the sampling distribution of sample mean has a mean equal to the population mean. So this is from section 5.4, the first learning objective, the property that we talked about. And remember, the standard deviation has a formula. It is population standard deviation divided by square root of the sample size. What is this? Oh, they gave us the variance first, which you will probably not really going to use. We're going to use this bottom one. So I want you to highlight this. This is an important one because if you are collecting a sample and try to figure out what is the probability that their mean is less than or greater than, then you have to use this standard deviation, not the population standard deviation. You're going to have to calculate this first. Okay? All right, let me go to the next slide. I think we're still talking about it. Example. Now listen, I don't know when to stop. I started from slide number 14 and it goes up to 37. So maybe I'll stop after slide number 28 or so, okay? I'm scared. Is it recording? Oh, yes, it is. Okay, so I'll go back and go over a couple more examples, but I don't want to make these videos too long, so I'll just do maybe a couple more in this video. Okay, example. Interpreting the central limit theorem. A study analyzed the sleep habits of college students. Do you guys sleep? I don't think many college students really sleep. The study found that the mean sleep time was 6.8 hours. I mean, for me, that sounds high. I thought some people sleep like only 4 hours, 3 hours. But that is the average. Okay, noted. Oh, with the standard deviation of 1.4 hours. Another number noted. Now, what they gave us is the mu and the sigma. You know how I do these word problems. Whenever I see them, I'll highlight these, and then I will write it down. Look at this for me, and I will use the appropriate symbols. I want to use the symbol for mu. I'm going to go to, see if I can go ahead and draw mu. Hey, there it is. And I do want to have a standard deviation too. All right. So they gave us that the mu is 6.8 and standard deviation is 1.4. Oh, did you just see that? That was so cute. Now, I'm going to show you. Look at that. I had a lowercase sigma, and when I hit enter, they changed it to uppercase sigma. Silly. I don't need an uppercase. I need a lower. Oh, did you just see that too? When I hit enter, they changed it to the big letter M. I don't need that. I need the mu. In fact, that's what I need. Okay, so I marked those two things that I was given because those will be useful. Mean and the population standard deviation. They said random sample of 100 sleep times are drawn from this population. I'm going to highlight this one too. This is important. What is 100? N equals 100. So these are the numbers that I need. Okay? They said find the mean and the standard deviation of the sampling distribution of sample means. Then sketch a graph of the sampling distribution. Now, I am looking at this ugly population distribution picture. Would you say this is normally distributed? I say not, because this is not symmetric. In fact, it even looks skewed to the right, and we got a long tail. Some students are sleeping 11 hours a day. What? That sounds... And some are sleeping like 2 hours. But, the population distribution is not normal. So what do I need to use? I'm going to use the central limit theorem here, you guys. I need a sample size greater than 30. The good news is the sample size is 100. So, yay! By the central limit theorem, the sampling distribution of sample means is going to be approximately normal, even though we are starting from this ugly population that is not normal. So, we just determined that the sampling distribution will be normally distributed. That means we can follow, let me go ahead and show you the formulas, okay? We can follow these formulas. The mean will be equal to the population mean. They gave us that the mean was what, 6.8? So that is going to be that. But we're going to need our little baby calculator to calculate the standard deviation of sample mean. We're going to have to divide the population standard deviation by square root of n. Okay, so get your calculator ready. We're going to type some things in. But I think I'm just going to go through this Google slide with you. Why not? Because I already have everything typed up. How about at least to make it look like we're actually doing this instead of just reading it from the slide, I brought it down here. Remember, we noted that the population standard deviation was 6.8. So that's why they're saying the sampling distribution will have a mean of 6.8 right there. You see that part right there, right? Now the hard part is figuring out the standard error, which means the standard deviation of the sampling distribution of sample mean. It's so long. The word is so long. You know that movie title? Planet of the Apes or the War of the that. It kind of makes it sound like it. But this is what they are doing to figure that out, the sampling error out. They're doing population standard deviation, which is 1.4 divided by square root of 100. Ta-da! So if you do 1.4 divided by square root of 100, which is 10, 1.4 divided by 10 will give you 0.14. So mean is easy, you guys, right? You just copy the same thing from the population mean. But for the standard error, you're going to have to use this formula, okay? So remember this, please, from that first learning objective. So let's go ahead and sketch this. We're going to put this 6.8 in the middle because that's the mean. And we're going to go up or down by a unit of 0.14 because that is a standard deviation. Okay, let's go to the next slide because we already have a picture of it. Here you go. So we plot that 6.8 in the middle. And with that small standard deviation of 0.14, we go 1, 2, 3 to the right and 1, 2, 3 to the left. I wish this graph or this, this graph has those those important points marked. And I bought a new computer, you guys, so I may try to show off my sketching skill. Hold on, where's my Apple Pencil? You don't really need this part, but I just want to play, you know. All right, hold on a second. I'm going to go ahead and connect it, and I will show you my drawing. 6522. What I am doing is I'm connecting my iPad screen so that I can draw with you. So I would do it this way. Like I put that 6.8 in the middle. And I will just draw my beautiful bell curve above. It's not really perfect, but I can never get it perfect enough. That's good enough for me. And I go 1, 2, 3 to the right, 1, 2, 3 to the left, and I figure this out by where did my slide go? And I figure this out by doing, okay, mean of the X bar was 6.8. Standard deviation of these X bar was 0.14, right? So I have to do 6.8 plus 0.14. So first number is 6.94. Next number is I add another 0.14, and that is 7.08 plus another 0.14, that is 7.22. So just like that, I would do it this way, actually figuring it out. And to go to the left of 6.8, I will subtract 0.14, 6.66, you guys, and minus another 0.14. And you get the idea, right? You can do it this way. And I like my picture even better because I have my important points plotted. Because I'll be able to say something like this. If I draw a sample of size 100, 95% chance that the sample will have, this is the 2 standard deviation point. This is 95% in there. There's a 95% chance that sample will have a mean in between 6.52 and 7.08. So I go out there and collect a sample of n equals 100. And if the x bar comes out to be, let's say, 8 hours, you notice how 8 hours is like way out there? That will tell me, oh, that is very unlikely. Maybe my sample was biased so that it gave me a very unusual sample mean. And this idea will connect to our the inference unit, which we kind of started with confidence interval the other day. But sampling distribution is what we use to do the hypothesis testing and the confidence interval. So what we are doing in 5.4 is very important because this is the basis of how we're going to do these confidence interval and the significance test. So you'll hear more about those later. Let me go ahead and close this. Stop mirroring. All right, I'm back to my computer. Okay, here we go. Let me do maybe, how long have I been going? Minimize the screen. I was recording for the 17 minutes. Let me do maybe 3 more minutes, okay? So they gave me a picture, but I say I can do a better job, so I tried it. And we talked about how to create a normal distribution graph. All right, one more example, and then I'll stop this video. The training heart rates of all 20-year-old athletes are normally distributed. That first phrase that I just read, the first part of the sentence that I read, they just told you that the population is normally distributed. That means I don't need a big sample size. It's like if the population is already normally distributed, the sampling distribution of sample mean is automatically going to be normally distributed. So I don't need to use n equals, we don't need the n to be greater than or equal to 30. That's what I'm trying to say. With the mean of 135 beats per minute and the standard deviation of 18 beats per minute. Random sample of size 4. And you're like, oh, that is so small. Oh, what's going on with my slide? N equal 4 is so small, but like, who cares, right? It's okay to be small because the population distribution, as you can see in this picture, is normally distributed. So we don't need a big sample size because we are working with a normally distributed population. Okay, the mean of each sample is determined. Find the mean and the standard deviation of the mean of the sampling distribution. Then sketch a graph of the sampling distribution of sample means. This is the same type of problem, isn't it? So now we're going to have to find the mean, standard deviation of the sampling distribution. So let me go ahead and highlight the clues here, okay? I'll go ahead and highlight the mean and the standard deviation and the sample size of 4. That's small, but that's okay because population is normally distributed. We don't need a sample size greater than or equal to 30. I'm going to go ahead and type these important information. I'll say I need a symbol for mu. Mu, and I need a symbol for standard deviation. I know mu is equal to 135, and I know the standard deviation is equal to 18, and I know the little n is equal to 4. These are the important information that we need to use to find the mean and the standard deviation of the sampling distribution. As you remember, the mean is the same. The mean of the sampling distribution of sample mean is just going to be 135. But I'll go ahead and do this on my calculator, and I will check this on the next slide. I'll do a fraction bar, and I'll type in 18 is going to get divided by square root of 4 by that formula. So the standard error better come out to be, what? That's too nice. Well, okay, is what it is, 9. So the answer is going to be 9. Let's go to the next slide to take a look. But if you're wondering where did you get that from, that's the formula. Remember, that's the formula. So let me present this. The sample mean should be the same. I like to copy this down here on my next slide. Oh, not that. I would like to copy this text box so that if you are just looking at the slide, you know where these pieces are coming from. For those of you who are not listening to this video, but just are going by the Google slide or textbook, the mean is 135 because it's the same as the population mean. But remember, for the standard deviation of the sample mean, we have to follow this formula. And just like how we got on the Desmo Scientific Calculator, if you do 18 divided by square root of 4, you get 9. So when you sketch this, you'll put that 135 in the middle, add 9 or subtract 9 to go to the right or go to the left of this mean. So I will not do it, but you saw one example of me doing it. I'll just give you a picture. So something like this. So if you get a sample of size 4, okay? Listen to me, I'll just say the story. If you could go out there and collect a sample of 4 and you found their average rate, and if it comes out to be 185, that means that's highly unlikely, isn't it? That means either the sample was biased, maybe that sample was not really good, it wasn't a good representation of the population, or there was something wrong, maybe you're lying. Okay, so that idea is going to be the significance test that we will talk about later. But I think I showed you enough in this video, so I will come back and talk about the next slide, slide number 23 to slide number 37 in a third video. I may probably do that tomorrow morning. I try to do it every day, but today we went over slide number 14 to slide number 23.